All right, hello guys. And today we are doing this ATP paper from the IGCSE course. So this is paper 61, summer 23. So again, a really recent paper. And also, if you guys have gone through my YouTube channel, so I just uploaded a video which solved the latest past paper that we have available for practice at this moment, which is March 24. And those summer 23 papers are really similar to the ones that's summer 23 paper, the most recent one. It's really similar to the ones that we had in 2023. So let's get started with this one. Again, I was having some troubles with the recording and stuff. So I have just solved all of this, and this is really going to be a walkthrough video where I go through my solution. So first off, question number one, a student investigates the balancing of a meter ruler. 1.1 shows the setup. So you have a load which is placed on either end of a metered rule and it's pivoted at the 50 cm mark. And with the scale of the ruler facing upward, so basically it's like laid flat down with its markings really on this top surface. He places an object Q with its center on the metered ruler at the 90 cm mark. Calculate the distance y from the center of Q to the 100 cm end of the ruler. So from 90 to this 100, this is your y, which would obviously be 10. But keeping into account that this can read to one decimal place, I would write this as 10.0. The student places a load P of weight 2 Newton on the meter ruler. He adjusts the position of the load so that the meter ruler is as near as possible to being balanced. So we know that in theory, we may say that the ruler balances, but this is very wishful thinking. This hardly ever actually balances. He measures the distance x from the center of P to the zero end of the ruler. He repeats the procedure using these different loads of weights 3, 4, 5 Newton. Values of P and X are shown in table 1.1. Describe the main difficulty that a student has when doing this experiment as accurately as possible. Now, you know that in any experiment which involves using a meter rule and basically balancing it, so it's really difficult to see where it's going to balance. And also, it's also really difficult to measure these distances because it's hard to judge the center of the load. Right? So these are the two main reasons why this experiment is basically it's a bit difficult to perform because of this idea, right? So if I just scroll down here, that's exactly the answer I've written. You were asked for any one. I've written both of these. So either you can say that judging the center of the load is difficult or achieving the balance is difficult. Plot a graph of y of p versus x. Draw the best fit straight line. So let's see if I can somehow make these points visible. So this is one point, this is another point, a third point. I think the fourth one is on the line. This is the fourth one, and there's a fifth one here. Just now not really visible because I've drawn over it now. Let's see if I can. No, I can't. All right, so if I take this away, so now the points are basically more visible. So you have 1, 2, 3, 4, and 5 as these different points. So when you do plot these points, it will immediately be obvious to use that this is not a straight line because of how the points are going. So this must be a curve. So then I draw this curve freehand. Again, just because it says the best fit line here does not necessarily mean you have to draw a line. A line can also be taken to mean a curve. Now here, because of how your plotting was, all the lines were basically, all the points were going upwards in a curve. So that's your understanding of how you have to draw a curve. So use the graph to find the value of x required to balance the ruler when p equals 3.5. So I just draw at p equals to 3.5, the value turns out to be 25.5 centimeters. Using apparatus from 1.1, explain briefly how you would determine the position of the center of mass of the ruler. So you know that the center of the mass of the ruler is basically where the meter rule would balance if none of the loads were placed, right? So with no loads where the meter rule balances, this would be its center of gravity or its center of mass. Again, this is really straightforward, I guess. Moments, experiments, moments, ATP questions are really straightforward. Question number 2, a student investigates the cooling of water under different conditions. 2.1 shows the setup. So there's the bench, there's a stand, and the thermometer, which is clamped, and this is a beaker. So the thermometer in 2.2 shows the room temperature theta R at the beginning of the experiment, record theta R. Now, obviously, the way this is, if I just zoom into here, so you have 10 divisions here between 10 units. So each division must be 1. So this is 1 after the 20. So this must be 21. Again, writing a correct unit where it's not written, this is your call. If you don't write it, it would cause you to lose marks. Student pours 200 cm cube of hot water into the beaker. She records the temperature theta of the hot water at time t equals to 0. She immediately starts a stopwatch. She continues recording the temperature at 30-second intervals. Temperature readings are shown. Complete the column headings. So time would obviously be in seconds. Theta would be in degrees Celsius. And then you have to complete the first column, which is the time column, because the theta column is entirely completed. So it's 30-second intervals. So from 0, I just have increments of 30 going on then. So 30, 60, 90, all the way up till 180. How far the table takes me, I go with those increments of 30. Calculate the decrease in temperature between 0 and 180. So we just subtract these values. That turns out to be 25 degrees Celsius. Part 2, calculate the average rate of cooling of the water using this equation, delta theta over delta T. Delta theta I just found out, delta T is given. I just use the formula, include the unit. So the temperature change was in degrees Celsius, and this is per unit time, so per second. Next, a student suggests that the average rate of cooling of the water decreases as the temperature comes nearer to room temperature. So just one change to the experiment that you could make to test the statement. So right now here you can see that the cooling does go down, like from 92 to 84. This is a pretty big jump, but then these jumps get smaller. So if you do this experiment for a longer period of time, then it's going to be much more obvious as to how the rate of cooling is changing, right? Next part suggests how to display the results. You see this word display, your mind should automatically be thinking of a graph. So you draw a graph and then you just need to see what the graph axes would be. So you can say it's a graph of temperature versus time. That is one possible graph. That's what I've written. Otherwise, somebody else could also suggest that this is a graph of the rate of cooling versus time. Both would be acceptable. Explain briefly why it is good practice to read the thermometer scale at right angles. Again, pretty basic stuff. You have to avoid parallax error, and you just describe this in any way possible. And this is your answer. Next, read the bottom. The student uses a measuring cylinder to measure 200 cm cube of hot water. She reads the scale at right angles, right? So you're reading this at right angles now. So for reading this at right angles, obviously, you are avoiding parallax error. What other precautions you can take while reading? So you can say you can read the bottom of the meniscus, right? This is one of the very obvious ones. Or you can also ensure that your cylinder or whatever you're reading this is on a horizontal surface. All right, question number 3 is on refraction of light. It's a full-blown question, which does talk about a lot of details that may be asked in similar questions. So student investigates the refraction of light using a semicircular transparent block. 3.1 and 3.2 are showing his ray trace sheet. So previously this was given on figure 3.1, draw the normal NL through the center of AB. So through the center of AB, you had to draw this normal. So you look at how much AB is and you just place your normal line, which is to be labeled NL at the center. Again, while drawing the normal, something else you should make is this angle to show that this is perpendicular. Obviously, you guys know that normals are perpendicular to the surface, forms a 90-degree angle. Continue the normal so that it passes through the curved side of the block, which I've done. It's also passing through the curved side. Label the normal NL. Label the point C where the normal crosses AB. So normal crosses AB at C. That's what I've also labeled. Draw a line DC below line PC at an angle of incidence 30 degrees to the normal and to the left of the normal. So PC was this line here. So DC is below that, and the angle of incidence is always with respect to the normal. So this angle is 30 degrees. And as you can see, this is also to the left of the normal. So you weren't supposed to draw it here. This is what the examiner is trying to tell you. Mark with neat crosses X for the positions for 2 pins on the line DC at a suitable distance apart. For this type of ray trace experiment, label the positions P1 and P2. So again, similar to how you have these pins labeled here. So there's one here, there's one here. You draw more pins here. Now, remember that I've made you guys do this experiment way back when we were doing light. This is how those experiments go. And if you read this question carefully, you also get a hint for what you have to write in a later part, which is that you are supposed to place these pins at a suitable distance apart. The idea is that to increase the accuracy of this experiment, the pins should be as far apart as possible. So even though I read this later, you should have drawn these pins even further apart to show the examiner that you do know that this is how you increase accuracy, right? But here the examiner was willing to award marks if you just have these pins P1 and P2 drawn on the line. This is enough for the examiner here. So in this case, they were supposed to be 5 centimeters apart, is what the examiner says. So actually, try to make this a bit like what the examiner wants us to do. Right? And then I pick this up. Let's get rid of this for now. Right? So obviously, your pen has to be on the outside of the block. That's obvious. It can't be inside the block. So that is how our pins look like in this case. All right, I think sharing is stuck again. Let me reshare. Right, so I think what you guys missed is just me taking these some further apart, some distance further apart, not really all that difficult. Label these pins P1 and P2, which I've done. Student looks from the position of the eye shown in 3.1 to observe the images of P1 and P2 through the side AB of the block. He adjusts his line of sight until the images of P1 and P2 appear one behind the other. You know that this is how we do the experiment. He is looking from here, as is shown, and he adjusts his viewing positions until P1 and P2 appear to be in the same straight line. He places 2 pins P3 and P4 between his eye and the block so that P3, P4, and the images of P1 and P2 seen through the block appear one behind the other. Positions of P3 and P4 are shown. Draw a line joining the positions of P3 and P4. Continue the line to AB. So this is what we were supposed to do here, which is again what we are always expected to do with questions of this sort, is that you just need to join the pins together. And you needed to continue the line till AB, and you had to label the other end E. Measure the acute angle between NL and the line CE. So the mark scheme was accepting all of these values. My value was turning out to be approximately, I guess, 48, or either it was 49 degrees. State one precaution that you would take in order to produce an accurate ray trace. So you should place the pins further apart, and also you should align and view the bases of the pins. Similarly, you can also say you should use a sharp pencil to make these lines. A student moves the transparent block to a new position on the ray trace sheet as shown in 3.2. He places pins P1 and P2 on the line DC in the same positions used in B2. He observes images of P1 and P2 through the curved side of the block. He places pins P5 and P6 between his eye and the block so that P5 and P6 and images of P1 and P2 seen through the block appear one behind the other. So this is exactly what we did in the previous part. He's just telling us that we do this for a transparent block in the new position. So this is where your pins would be, and this is somewhere where you would be seeing the pins, and you just look at those. What you are asked to do in this one is to measure the acute angle beta between the line AB and the line CF, which is this one. So this turns out to be, it was 72 degrees for me. Examiner is accepting 70 to 73. Calculate the angle theta between line CF and the normal. So this angle right now is 72. They're asking us for the angle between the normal and CF. So because this entire thing is 90, so 90 minus this thing is going to give us that angle, which turns out to be 18 degrees. Now, a student suggests that the angle alpha should be equal to the angle theta. State whether your results support the suggestion and justify your answer. So theta was 18 and beta was, and alpha was 47, was 48 for me. So again, these are obviously not close to one another. So I just show here that the percentage difference between them is greater than 10%. All right, last part is a planning question. So do go through this. A student investigates the change in resistance of a lamp filament when the current in the lamp is increased. The following apparatus is available: a power supply, low voltage filament lamp, ammeter, voltmeter connecting wires. Other apparatus normally found in a school lab is also available. Plan an experiment to investigate the change in resistance of the filament lamp when the current in the lamp is increased. Resistance is given by this equation. V is potential difference, I is current. You should draw a circuit diagram of the circuit used. So this is not very difficult if you think about it. For the resistance, I would need the voltage across the filament lamp and the current through the filament lamp. Explain briefly how to do the investigation, including how to change the current. So if you look here, we did not have any sort of equipment here which is allowing us to change the current, right? So here you have to talk about what you should use to change the current, right? One of the most obvious ways is to use a variable resistor, right? That's how you can change the current, and draw a table or tables to show how you are going to display your readings. Explain how to use your readings to reach a conclusion. So this is where the recording messed up. I was somewhere here. This is how the circuit diagram is supposed to look like. Again, label everything. This is your battery. This right here is your variable resistor. This is your lamp. The voltmeter is connected as it should be in parallel. And this is your ammeter. So now, again, let's define the problem. What are we changing here? We would be changing the variable resistor, the resistance of the variable resistor, and thereby changing the current. And we would be measuring the voltage across the voltmeter and the current through the ammeter, right? So that's how we are going to measure the current here. So let's see what I have to say now. So I'll say this, that we will vary the current in the circuit by varying the resistance of the variable resistor. So this is really our independent variable here. And we will measure current and potential difference across the lamp, right? And later you can also say that using this equation, because this is what you aim to do here, you want to see how resistance changes. So using R equals to V over I, we will calculate the resistance. And always do write this point on how many readings you are supposed to take. So repeat for at least 6 different values of the resistance. So that will obviously also give you 6 different values for the voltage and the current, right? So this thing, only saying it up to here, does gain you like more than 50% of the marks here, because the next marks are just for talking about the table of values and just talking about how you draw the conclusions, which are obviously always the same each time out. So this is my serial number column. Again, not mandatory, it's up to you. Serial number column, and I would obviously have the resistance of the, oh, so I have to think about the current and the potential difference, because that is what leads us to the resistance of the filament lamp. There would be the current in amperes, right? This is for the filament lamp. There would be the voltage in volts, and using R equals to V over I. So R in ohms, which basically comes about from V over I, right? And now how to reach the conclusion? So you'll just say this, that plot a graph, because you wanted to see what? You wanted to see how the resistance changes with current. So you'll say plot a graph of resistance versus current, right? If you say voltage versus current here, even though that is technically a correct graph, that would not get the mark here. So plot a graph of resistance versus current, and you draw your conclusions from this. So if you guys have any questions till here about any of the parts, I'll be more than happy to take them. Again, you guys would be feeling a bit more confident, obviously so close to your exams, because you've been doing a ton of practice and you know now the type of questions which are asked and also how to respond to those questions. So this was summer 23, paper 61. You guys are supposed to do paper 62 of this IGCSE paper as your homework. All right. Then we have a class day after tomorrow in which we are going to do the same for winter 23. And on 12th, we have a revision session plus a guest paper planned for 12th. And the timings for that are 1 to 2:30, right? That's what we'll be doing in the session that day. So if you have no more questions, I think we can call it a day. So take care, guys.